So today we're looking at aldehydes and ketones. So in a sense, the last homologous series that we looked at in the AS content was alcohols, and from alcohols we were able to make aldehydes, ketones, carboxylic acids, depending on which type of alcohol we had to start with, whether it was primary or secondary. And the beginning of the first homologous series that we look at in the sort of post-AS content is regarding those products, is regarding aldehydes and ketones now, and in the future we'll also be looking at carboxylic acids as well as their derivatives. So first of all, we're going to recap the oxidation of alcohols, because that's how we make aldehydes and ketones. So if we have a primary alcohol, we can make an aldehyde, and if we have a secondary alcohol, we can make a ketone. And we achieve this oxidation using acidified potassium dichromate. So the acidified bit is a fundamental part of the reagent's name. So if you're asked to name the reagent suitable for oxidizing primary or secondary alcohol, you must say the acidified part of the name. You must include either H2SO4 or say acidified or say H+ ions, as well as the potassium dichromate. Now, the reason why it's necessary is if we consider the half equation, the half equation in which the chromium is reduced from +6 to +3, then when we constructed the half equation, we would have had 14 H+ ions, and that is the reason that we have to have acidified potassium dichromate. Without those H+ ions, the chromium wouldn't be reduced from +6 to +3. When we're looking at primary alcohols, we can have full or partial oxidation. So if we have partial oxidation, that's going to result in an aldehyde. And if we have full oxidation, then we're going to get carboxylic acid. So which one we get, or which one we're aiming for, or how we go about getting the one that we want, would be through the experimental method we use. So if we want an aldehyde, then we'll use distillation. And that's because as the aldehyde is produced, it will have a lower boiling point than either the primary alcohol or the carboxylic acid that might also be produced. And so because it has a lower boiling point, we can distill it off, basically. So we can, as it's formed, we can distill off the aldehyde product and collect it. If we want the carboxylic acid, then really we want to make sure that the reaction goes to completion. We want to really encourage that, so we reflux the reaction mixture, which basically means we heat it constantly until the reaction is complete. With the oxidation of secondary alcohols, that can only result in a ketone or ketones. So we can just reflux that, because again we want the reaction to be complete if that's our intended product. And just to remind ourselves that with tertiary alcohols, oxidation can't take place, and so there will be no reaction between acidified potassium dichromate and a tertiary alcohol. So when we're wanting to check what we've made, or to confirm that what we've made is what we think it is, or if we're given two unknown substances and are told one's an aldehyde and one's a ketone, then we can do either of these two tests to confirm whether we have the aldehyde or the ketone. So Tollens reagents. So Tollens reagent has Ag+ ions, silver+ ions present. And so what's actually happening when you react to Tollens reagent with an aldehyde is that the aldehyde is actually oxidized to the carboxylic acid. The fact is, an aldehyde can be oxidized further. If that's being oxidized, then what happens to the silver the silver ions are that they are reduced. So they go from being Ag+ ions to Ag metals. So we get that silver mirror formed. Ketones can't be oxidized any further, so we don't see any change in the solution. It remains colorless. Fehling solution is an alternative. So it's the same principle. An aldehyde can still be oxidized, which means something in the other reagent can be reduced. In this case, it's copper. So it goes from copper 2+ to copper 1+. We get a red precipitate formed if there's an aldehyde present, and if there's a ketone, there's no change, there's no reaction, so the solution remains blue. So we've talked about making aldehydes and ketones from alcohols, and that is oxidation. But actually, it's possible to reverse the process. So it's possible to go from an aldehyde to a primary alcohol and from a ketone to a secondary alcohol. And it's the opposite of oxidation, so it's reduction. So it's when reduction is the conversion, or the converting back of aldehydes and ketones back into alcohols. So again, we can have a sort of an old-fashioned definition, in which case, where we talk about the loss of oxygen or the gain of hydrogen. We can also do it by following or tracking oxidation numbers. But in this instance, actually, we're going to focus on the gain of hydrogen. So at A level, we use, to represent the reducing agent, to represent the source of hydrogen, we use H with the square brackets, just like with oxidation, we used O with square brackets. And then in terms of writing the reaction equation, we obviously are starting with whichever aldehyde or ketone it is that we are trying to reduce. And then we've just got to think or consider, well, what primary or secondary alcohol would that make? So you can start sort of, if you're trying to write this from scratch, write the formula of the aldehyde or the ketone, and write the formula of the product that you expect to get, either the primary alcohol or the secondary alcohol. And obviously you have to give some thought about what that structure will actually be. And then it's just a question of balancing it in terms of hydrogens. So there's just a sort of visual representation of the fact that we can oxidize primary alcohols to an aldehyde, and we can reduce aldehydes to primary alcohol, and we can oxidize a secondary alcohol to a ketone, and we can reduce a ketone to a secondary alcohol. And, you know, I'd ask the question there, why is tertiary not here? Well, we know from the alcohols topic that you can't oxidize a tertiary alcohol, and therefore there is no possible product, so therefore there is nothing that can be reduced back to a tertiary alcohol. So even though we use H with the square brackets to represent reducing agents, when it comes to the exams, we still need to be able to name suitable reducing agents. And two that are commonly mentioned in terms of the reduction of carbonyls are lithium aluminium hydride, which has the formula LiAlH4, and sodium borohydride, which has the formula NaBH4. And so you can see the fact that they are ionic compounds, and you can see sort of the ions at the bottom of this slide. That's not really that important. It's not really something that you get quizzed about, but it's just really to maybe help you better appreciate how these compounds are comprised. Now, lithium aluminium hydride is a particularly powerful reducing agent. It's actually reacts. It's a very vigorous reaction with water. It's a potentially dangerous reaction. A lot of hydrogen gas is produced rather fast, and as we know, that hydrogen gas is a flammable gas. So one of the things that we have to be very careful about is the solvent that it's dissolved in. And so what we use is a solvent called dry ether. There are other possibilities, but in terms of what may ever be mentioned in your A level, then dry ether is the one to go for. Its UPAC name is diethyl ether and has the structure that I've drawn here. So we've got two ethyl groups, and that hence the diethyl. And then how we can recognize it as being an ether is because the oxygen is between two carbons. So that is the functional group of an ether molecule. Sodium borohydride is not as powerful a reducing agent. It will react with water unless it's alkaline. I seem to have repeated this twice. But anyway, at A level, you will often see it just simply stated as AQ, aqueous. So really, in terms of the conditions, you would just write aqueous. But if we were to sort of expand on that a little bit more, we might use an alkaline solution as a solvent, or we might use methanol or ethanol, or we might use a mixture of water and alcohol. But like I say, at A level, as far as you're concerned in an exam question, you can simply state it as AQ. All right, so I want you to sort of pause the video and have a think about what's on the screen here. So it says name the carbonyl or alcohol related to the chemical on the left by oxidation or reduction. So if ethanol is oxidized, what's it oxidized to? If propanol is reduced, if propanol is reduced from something, what's it reduced from, and so on. So I'll let you have a go at that, and then I'll write the answers. So hopefully that was relatively straightforward. There was a little bit of repetition there, but hopefully you didn't have any real problems with that. Okay, so the carbonyl group is the functional group of the aldehydes and ketone families. So we need to appreciate a little bit more the features of that make it the functional group and how that affects its chemistry. And so the first thing that we just need to consider is the fact that we are talking about a carbon-oxygen double bond. And as we learnt with alkenes, the sort of second bond of the double bond is actually called a pi bond. So, and a pi bond is an overlap of electrons in adjacent p orbitals. So what we've got here is we've basically got an unpaired electron, if you like, in one of the p orbitals on the carbon, and an unpaired electron in the p orbital of the oxygen. All of the other bonds are basically pairs of electrons. So there's the sigma bond there. Maybe actually I might just redo this one slightly, just make that a bit more consistent. And just as with alkenes, what actually happens then is those two single electrons become delocalized between the two atoms, forming a pi bond, forming our second bond, forming our second pair of shared electrons. Now, oxygen is a more electronegative element than carbon, so what we actually get is a slight distortion of the electron density, where it's drawn towards the oxygen atom because that's the more electronegative atom. Remember, electronegativity is the power or ability to attract a pair of electrons in a covalent bond. So we have, as a result, we get a delta plus and delta minus. And as we already know from halogenoalkanes, for example, having a delta positive carbon can have a significant impact on the reactivity or chemistry of a particular type of compound or particular compound. And given its delta plus, the carbon is delta plus, and if we remember with our halogenoalkanes, a delta plus carbon made it susceptible to attack from nucleophiles. That's exactly what we're also going to have here. Something else just stress at this point, because it's going to become important or become relevant, is that if we look at the shape of the molecule around the carbon of the carbonyl bond, what we can see is it's trigonal planar. The fact it's planar is going to be a very significant later in this video. The consequences of it being planar are going to be very significant. And the trigonal part just really tells us that we've got 120 degrees bond angles. But really the key point here is the fact that it is a planar functional group. So the delta positive carbon is susceptible to attack from nucleophiles. And in this particular case, what we get is nucleophilic addition. So the reducing agents that we looked at before are sodium borohydride or a lithium aluminium hydride. What they're going to be is a source of hydride ions. And so hydride ions are not something I don't think you've ever come across before. So they are H- ions. So what that means is that we have hydrogen with 2 electrons. And then really we should put the brackets and the minus charge there. So they have a lone pair of electrons, they have a pair of electrons, and our definition of an electrophile is a electron pair donor. So looking at the actual mechanism itself, we have our hydride ion. We must show that pair of electrons because it's the movement of that pair of electrons that we're showing when we draw the arrow. So we draw an arrow from that pair of electrons on the hydride ion to the delta positive carbon of the carbonyl group. And then something that's a little bit new is that in terms of showing on the mechanism, the pi electrons move on to the oxygen. Okay, so the pi electrons move on to the oxygen. So what we get as a result in the second structure in this mechanism here is that the hydrogen has now attached to the carbon, and we just show the lone pair of we show the pair of electrons that have moved onto the oxygen as a lone pair. And of course, what we've also got to recognize is that we now don't have two electrons being shared between the oxygen and the carbon that were in the pi bond. We have both of them on the oxygen. So we also have to show the fact that it is negatively charged, that part of the molecule. And then those pair of electrons will attack an H plus ion, and that has come from a dilute acid. Okay, so when we're thinking about our reagents, we need our reducing agent and a dilute acid, or followed by a dilute acid. So we need a source of H minus ions, that's the reducing agent, and then we need a source of H plus ions, which is the dilute acid. The oxygen and the hydrogen form a bond, and we get an alcohol. So there is our reduction. We've gone in this particular example from a ketone to a secondary alcohol. And we can see at the bottom, we can represent that equation as we saw earlier. So in this topic, we're focusing on, or the mechanism, that we're focusing on is nucleophilic addition. And we really only apply that to two reactions. One is this one, which is the reduction of our aldehyde or ketone to make either our primary alcohol or secondary alcohol. And then the other reaction that we look at is a reaction with cyanide ions. And that, just like we saw when we did halogenoalkanes, one of the reactions that we saw was, or one of the nucleophiles was a cyanide ion. So here's just a bit of information about cyanide. We don't really need to know this detail. What we will need to know is why we don't actually use hydrogen cyanide as a source of our cyanide ions, but and in a sense to place that into context, that's why we've got some of this information. So hydrogen cyanide is a colourless and extremely poisonous gas. So it's quite a famous. It is quite a famous poison, basically. You can see here we've got some concentration examples, so 300 milligrams per meter cubed. That will take, if you're exposed to that for an hour, you would die, the average human would die. If you have 10 times the concentration, then it's going to take under a minute. So obviously a very toxic, very extreme, a very poisonous gas. And yet we still make quite a lot of it. And one of the reasons for that is that, it's going to be important in the production of what we do actually use in our nucleophilic addition reaction, which is sodium cyanide or potassium cyanide. But they are also used in gold mining. The organic synthesis obviously is what we're looking at. And also even the production of polymers such as nylon. So as awful as it is, it's still something that we use quite extensively in various parts of industry. So instead of using hydrogen cyanide as our source of cyanide ions, we're going to be using sodium or potassium cyanide, and we're also going to be dissolving those in a dilute acid, because we are actually going to need the H plus ion as well as the cyanide ion. So the combination of the sodium or potassium cyanide dissolved in dilute acid gives us the H plus or cyanide ions, and that's going to allow us to make hydroxynitriles from aldehydes or ketones. So just before we look at the actual mechanism, let's just have a little bit more information on nitriles. So, we have written, when we did halogenoalkanes, the cyanide ion. Now, when the cyanide is part of a organic compound, if we're able to use it as the suffix, if that's how it works in terms of priority, and frankly at A level we only ever use it as a suffix, then it's no longer called cyanide but is called a nitrile. And so we're now thinking of it as a carbon triple bonded to a nitrogen, and the carbon also having a single bond as well. So when we come to naming it, we've got here the suffix is nitrile or the prefix is cyano. Well, cyano is not going to be a feature at A level, so we're just only concerned with the suffix. And if we've got a very simple compound where we just have the nitrile group and then a carbon chain, and assuming it's saturated, we basically just name it in terms of the number of carbons as an alkane. So in this example, ethane, and then we just add nitrile. Okay, so key thing to mention is, firstly, it's all one word. So remember when we did nomenclature, words, there are no gaps, there's no separation between words. Between numbers are commas, and between numbers and words are dashes. And very important in terms of making sure you get the mark in an exam is you must include the E part in the middle, the ethane. So if you wrote ethanitrile, you wouldn't get the mark. Okay, so that's very important. Something else to just highlight to make sure that you've got here, when you're naming the compound and you're thinking about the most consecutive carbons when you're trying to work out your sort of like stem part of your name, you do include the carbon in the nitrile group. So that is why we have got ethane nitrile there, and why we have got propane nitrile, and then why we have got butane nitrile. So please make sure you appreciate that, because that's where sometimes people can get caught out when naming compounds with nitrile groups. So here's the mechanism, and so it is exactly the same mechanism, right? It's a nucleophilic addition. We are drawing the same arrows. The difference is that our nucleophile is different. That is the only thing. And of course, when it comes to the reagents, because we have a different nucleophile, we have to have different reagents. So we've got a cyanide nucleophile. So we absolutely must include the lone pair of electrons on the carbon, and we must include the charge. So then we're showing an arrow, which is the movement of that pair of electrons towards the delta positive carbon. So it's an electron per donor. Again, remembering, that the pi electrons, not that you have to refer to them as the pi electrons, but a pair of electrons in the carbon-oxygen double bond moves onto the oxygen. We show that pair of we must show that pair of electrons, so we show one of the lone pairs on the oxygen, and also that means that in effect the oxygen has an extra negative charge, so we need to show that it's negatively charged, and then that part of the molecule, that pair of electrons on the oxygen, is going to move to an H plus ion and form an OH bond. So we said we were making a hydroxynitrile. So hydroxy is the prefix version of an alcohol group's name. I didn't really phrase that very well. So because nitriles take priority over alcohols in terms of names, and it being the suffix part of the name, we now refer to this as a hydroxynitrile. Okay, and that will also therefore need to be taken into account when we're writing the name out. So here's a specific example. So I'm starting, and I'm trying to highlight a few things as we go along. So we just got ethanol. So we picked a fairly simple compound. We're doing nucleophilic addition where the cyanide is acting as a nucleophile. So it's a lone pair donor. And so we get our hydroxynitrile at the end. And then thinking about the name, we started off with a compound with 2 carbons. When it comes to the naming of the product, we've now got a compound with 3 carbons. And that's definitely something to watch out for once the whole A level is over and you're doing synthesis questions, which are where you've got a number of steps taking place. So you're starting from one type of compound, let's say an alkane, and then 4 steps later, or there are 4 reactions, and you've got to work out what those reactions are to get the very final product. Something to look out for is if you get a change in the number of carbons, particularly it's changed by 1 carbon, then there's a high probability that you've had a nucleophilic reaction with a cyanide ion. So we got 3 carbons. Okay, so we've got our 3 carbons, so it's going to be propane, and it's propane nitrile because the nitrile is the suffix, it's the main functional group in our name. We have an OH group on the second carbon, so because nitriles take priority in terms of naming, then that's going to be a hydroxy, and it's on the second carbon, so it's 2-hydroxy. So the molecule that we've made here is 2-hydroxy propane nitrile. So notice all of the words are together. There are no gaps, no spaces, and that we're between the number and the word, we have a dash. Now, do you notice anything interesting about the products, bearing in mind perhaps not what we've learnt in this lesson, but maybe what we learnt in the last lesson? So I'm hoping you can see that we have 4 different groups attached to a carbon, which means that we have a chiral carbon, which means that we have optical isomerism. Now, it doesn't follow that optical isomerism comes about every time that you react a cyanide nucleophile with a carbonyl compound, so a ketone or an aldehyde. It does come about if the carbonyl compound is a ketone, and then it also comes about if the carbonyl compound is an asymmetric ketone, i.e. When we look at the carbonyl group, the alkyl groups that are attached to the carbonyl group in a ketone are different. Okay, so let's just look at that a little bit more closely. We are looking at nucleophilic addition, and the nucleophiles in question, as far as our A level is concerned, are either hydride ions, H- ions, or cyanide ions. And in terms of what they could react with, they can react either with an aldehyde or a ketone, but I'm going to split the ketones into symmetric and asymmetric ketones. So I'm going to think about 3 possibilities: an aldehyde, a symmetric ketone, an asymmetric ketone. So that's what I've represented underneath each nucleophile there. So I've got an aldehyde, let's do that. I've got an aldehyde, I've got a symmetric ketone, so we've got 2 R groups, and those R groups are the same. And then I've got an asymmetric ketone, so I've got an R and an R dash group. So that's to represent the fact that they are different. And if those 2 R groups are different, that means it's asymmetric, or it doesn't have a line of symmetry through the carbonyl group. And then I've repeated that with the cyanide. So let's consider what we would actually make if those reactions took place. Okay. So our aldehyde has produced a primary alcohol, our symmetric ketone has produced a secondary alcohol, and our asymmetric ketone has produced also a secondary alcohol. But there is a difference. So we can see straight away with the aldehyde that we have 2 hydrogens attached, so there cannot be any optical isomerism. Okay, not optical. If we look at the symmetric ketone, we've got 2 R groups that are the same. So we've got 2 of the same group attached to a carbon, so that is not optical. But if we look at the asymmetric ketone, we actually have 4 different groups attached to that central carbon. We've got a hydrogen, an R group, an OH group, and an R dash group. So we get optical isomerism in that instance. If we look at the cyanide now and think about what the products would be in if the cyanide acts as a nucleophile with the aldehyde, the symmetric ketone, and the asymmetric ketone, we can see that with the aldehyde we have produced a molecule with 4 different groups attached to the central carbon there, so that is optical, or would show optical isomerism. With the symmetric ketone, we've got 2 R groups that are the same, so that is not optical. And then finally with the asymmetric ketone, we have 4 different groups. We have R, OH, R dash, and CN, so that is optical. So you've got to be, there are no guarantees, You have to think about it carefully, think about the products. But there is definitely the possibility of optical isomerism when you do nucleophilic addition with aldehydes and ketones. Now, if you remember when we did the optical isomerism video or lesson, we talked about something called a racemic mixture. And that's where we had a pair of optical isomers in 50-50 proportions. Those isomers, don't forget, were also known as enantiomers. So that was a racemic mixture. And the consequence of that was that if we put a sample with a racemic mixture in it into a polarimeter, even though we had two optical isomers, we would see no rotation of the plane polarized light because they would cancel each other out. And I think I mentioned that racemic mixtures often happen in lab reactions, and this is an example. So we've seen that we should be making optical isomers in certain instances with aldehydes and ketones undergoing nucleophilic addition. But we do in fact get a racemic mixture whenever optical isomers are actually formed. And that is because of the way that the molecule is attacked by the nucleophile. So this is going back to earlier in the video when I stressed that it was going to become important, or it's going to become very relevant, that the shape of the molecule around the carbonyl group was trigonal planar. Before we carry on, this is something about mark schemes when they're asking you to explain why racemic mixtures come about. They are quite fussy, and there's certain things they don't like to see. So one thing that's always acceptable is if you're trying to describe the fact that it's planar, what you must say is that the carbonyl group is planar, okay? Or you say there's a planar carbonyl group. That's the way to phrase it. Anyway, because it is planar, and I'll show you this with an illustration in a second, because it's planar, that means that our delta positive carbon, which is going to be attacked by the nucleophile, there's an equal chance that it's going to be attacked from above as there is from it being attacked from below. It's like 50-50 chance. And whether it's attacked from above or below is going to result in one of the enantiomers. So the fact that there's a 50-50 chance means that we're going to get 50% of one enantiomer and 50% of the other. So here's a diagram to try and show you this. We've got our planar molecule. I've kept this fairly simple. So we've got our planar carbonyl group. And we've got a delta positive carbon there because of the carbon oxygen, because the oxygen is more electronegative. Our cyanide nucleophile is going to attack that delta positive carbon. It could be from above, it could be from below. If it's from above, we're going to get this structure at the end. And if it's from below, we're going to get the second structure. And as you can see, or hopefully see from the way I've drawn them, they are mirror images of each other. They will be non-superimposable. They are optical isomers, and they are going to be in 50-50 proportions. So if we were able to separate them, each enantiomer would rotate plane polarized light, and they would do so in opposite directions to each other. But what we're actually making is a mixture of 50% of each of them. We're making a racemic mixture. So what we'll find is that the plane polarized light is not rotated because those respective rotations cancel out. So I think I mentioned in the optical isomerism video that no rotation does not prove that optical isomers are not present, because there is always the possibility that there is a racemic mixture. So you need to think about the actual reaction that took place, or how our products, or how your product was actually formed. But this is one area which is a relatively common area to be questioned on in an exam. So they can ask you to have done a mechanism of nucleophilic addition reaction, and then they could be asking you about why does it not rotate plane polarized light, or something along those lines. So to end, we're just going to look at something because I think this will make more sense now that we've just done the nucleophilic addition reaction. We're going to look at something that isn't actually about carbonyls, but is about forming racemic mixtures. So there is one other area of the course in which racemic mixtures could have been made, and that is something that we did in part of the AS content, although the idea of racemic mixtures would never have appeared in that. And that is where we have electrophilic addition with alkenes. Okay, so let's look at an example. So I'm going to draw butene, and we're going to have it reacting with HBr. So we're going to have the pi electrons attack the delta positive hydrogen of HBr, and then the electrons covalently bonded between the hydrogen and bromine are going to move on to the bromine. So that gives us the following carbocation intermediate. So if we look at that and consider its actual three-dimensional shape, it's going to look like this. So we can see that it's got a trigonal planar shape around the positively charged carbon, and that means that our bromide ion could actually attack from above or below, in which case we would get two enantiomers as our product. We would get a racemic mixture. We have our attack from above or below, equal probability, so we would get 50% of the product would be with the bromide having attacked from the above, and 50% of the product would be from having the bromide attack from the bottom. We would get two enantiomers, but we would get a racemic mixture. So I just wanted, having sort of explained how we can get a racemic mixture in the context of carbonyls, because they relate to the same thing about this trigonal planar shape, the fact that we can have equal chance of attack or above or below. I just wanted to highlight the fact that racemic mixture can come from electrophilic addition with alkenes. It wasn't something we would have done at AS. It would never have featured in AS, but it could be something that could feature in your final A level. So I hope that's all been clear, but please do let me know if you have any queries.